to the Galaxy. It's an institution already. It's not just books. If you don't know, it doesn't matter. If you do, you'll love the references. We'll begin by the mandatory slides to tell you about the company I work at. It's Allegro. We do machine learning and deep learning lifecycle management. What it means for you is that we're a serious company and we have a very good open source solution that you should check out. Not only you, but many other big and small and companies and universities are using both our free and paid versions. So we must be doing something right. Now, this time it's going to be a little bit different because if you heard about hyperparameter optimization, you know that there are plenty of webinars out there that you can check out. And I looked at all of them and tried to find something that is complementary, something that you will be going and rewatching as you become more and more adept at this subject, because it's something you grow into. Okay, so it's exactly, if you know the Hitchhiker's Guide to the Galaxy, that's what it's supposed to be. So we begin with a mostly harmless introduction to hyperparameter optimization. And then we're going to learn a little bit, or remember if you were in my previous sessions, about research MLOps. Don't leave home without it. Then I'm going to give you a very detailed shopping list of what you should have if you're going to do hyperparameter optimization. Then I'm going to have a philosophical bit where I'm saying that hyperparameter optimization is basically pure research. Finish off with some warnings and then recommendations for the rest of your journey in hyperparameter optimization. Now, even if you don't understand anything or you don't want to listen and you're just watching this in the future and you're going to stop this recording playback right now, please look at this slide, okay? Hyperparameter optimization costs time and money. It's expensive. And if you try to do this in your organization and you do it haphazardly and you fail, this will have a transformative effect, okay? This will cause the organization to become one of those that I actually met, that they're saying, you know, we don't need searchers doing research because it's not worth it. We only do it when we go to production. And I've seen several of these. I don't know why. And basically, they all have one thing in common. They have this guy working for them who he knows how to give you the accurate models, but he doesn't know how he made them. Okay, so don't panic. This is, as I said, a non-conventional lecture about hyperparameter optimization. And we begin with an explanation of what is a hyperparameter. Well, hyperparameter is such a broad concept that it's easier to explain what's not a hyperparameter, especially when we're doing a process where parameters are being optimized. Okay, so anything that depends on the input data, or anything that changes during the run because of the input data, or anything that does not relate to the run, or like, for example, runtime, wall clock time, that's not a hyperparameter. All the rest is a hyperparameter, including the day you start your run on, and that's something I can tell a very weird story about if we have time. And also the network architecture, which is something we won't talk about because it's a completely different, a huge realm about network architecture searches. Okay, so that was easy. Now I want to take you to space. And in space, there is a guy, we'll call him Arthur Dent, and he wants his AI on the ship to prepare him chocolate chip cookies. And the ship does not know about chocolate chip cookies, and Arthur needs to explain what cookie is. And the ship understands that it's going to be a mixture of sugar, flour, and butter, and maybe some other things. But it doesn't really know. It doesn't really know. My connection keeps pressing. Oh, sorry, just a second, Bill. Okay, I'm going to send you a link to the presentation now. I think we have some technical difficulties. So just in case you're all breaking up, if you want to continue watching this in the future. Okay. Here is the link to the slides. You can join now. Okay, where were we? Yeah, right in the beginning. I will keep the chat window open. You just make it smaller. Sorry for the delays. All in a day's work. Anyhow, so we have a computer that needs to understand how to make cookies, and he doesn't know anything about cookies. So he will, this AI probably will detail all the kinds of ingredients in the recipe, and these will be hyperparameters that he needs to find the amounts of in order to make the cookie. So the sugar, the ratio between white and brown sugar, butter, egg, flour, the chocolate amount, the chip type, whether it's dark chocolate or white chocolate. And then there will be things with small amounts that he will mark in a different kind of type of hyperparameter, like baking soda, maybe vanilla, salt. And then there will be cooking instructions. And he will look at the cooking instructions in many, many recipes, and he will see that the baking temperature kind of changes with the recipe. Baking time never is told. It's always cook until brown. So this will be the parameter space. It will need to be optimized and found by the computer. And now, I haven't talked to you about optimization yet, so let's do that now, okay? The first thing first is not doing any optimization. It's going in a predetermined route, okay? Those of you from chemistry will immediately recognize this representation. This is a way to do grid search with 3 dimensions on a 2-dimensional space. It's a mapping, but it's and it's actually from a scientific paper about cookies and the amount of flour that you need to put in. And there's a link here. But the thing is that you do these grid searches when you know that there will be some kind of relevant combos that you need to scan out. It's not really giving you any more information than that, unless you don't know what the metric is. And then this computer doesn't know what taste means. So the computer will put on all the combinations, and you will have many, many different metrics, and you will choose one to represent taste. I don't know. So grid search, which is this, is really uninformative, and also it takes very, very long to visit all the spots. And if you see here in the image, actually it's very interesting to visit this spot, and the grid is not with enough resolution to visit it. Okay, the algorithm for this search is very easy. It's get parameters, get a recipe, run expensive evaluation, bake, get score, taste, and decide if you were done or not. If you're not done, you go back to 1. And in the case of a grid search, you're not done until you finished all the grid points. What would be a second option? The second option is, is telling I have no idea what combinations to try. If I don't have any idea, the only idea is to do a random search. If I have some idea, I can maybe put constraints on the ranges. For example, in this case, the computer was looking for the ratio between egg and the mixture of flour, butter, and sugar that he found. And eggs, they don't come in very well defined weights, so there's a lot of noise. So it's a random search, And looking at these searches, you can see that there's kind of some like two places, one where you have a metric going to 0 and one where there's a maximum. And when you go far enough out, you just get an omelet because you're just doing eggs with some flour in it. Also, this is not real research, okay? It's something I plotted just for making the example. And this is what you do with random search. Also, you need a lot of eggs for this, right? This is 120 eggs. What happens if you only use 12 eggs? Well, I reran the simulation and got only this space, and also the representation is completely off. Okay, this is the same formula that we're trying to find, and we put too few points, and we didn't find anything good. So, random search means lot of attempts. And actually, even though there were many random attempts, the final results were following the quote, almost but quite entirely unlike chocolate chip cookies, which means that there was a failure. The result was not what was looking for, and the whole time and efforts that was spent went down the drain. So, rethinking it, the AI assumes that now I need to do some even bigger research, and now time and money is going to be an issue. So since the random search failed, maybe don't go on random. Since the grid search takes a lot of time, maybe don't look at all the points. Maybe we should make sure to check all the areas in our sampling. Maybe we missed something. And also, since many cookies burned, and many cookies we knew they're not going to be tasty, maybe we're going to do some early stopping. But finally, I need a good result. Okay, so who knows what's between grid and random searches? And the answer is not money burning. Well, it is also a good answer, but it's not the correct answer. And what's inside is optimization. And since we're all in machine learning, I think that we don't need to expend lots of time about what it is. So let's do the basic definition. You have a function, and you want to find an extremal point, either minimum or maximum, by doing a systematic search from your allowed set, where you're going to put values, evaluate, and do something about it. The mouse is trying to find the cheese. The cheese is on top of a mountain. You can take different routes to find the cheese, and he has to stop in positions along the route to smell and see where the cheese is. So these are two different optimization approaches that the mouse can take. Actually, one of them is gradient descent, and the second one is the basic Newton-Raphson. But we don't care. Why? Let's see. First of all, we don't have a mountain. We have a very complex function. That actually we don't know the closed form, or if we did, it's just too busy to calculate derivatives for, etc. So we need a method that doesn't care about this. We need a method that only needs to evaluate the function given an input value. And moreover, since there are going to be dozens of those, we're going to first be doing something I call a double black box optimization. It's when you don't know the function and you also don't understand the optimization mechanism. I mean, when I first used, for example, Adam optimization for finding something, I didn't really understand what I was doing, okay? But it worked. So then I went and saw what Adam is. The same thing here. You will try stuff, and once it works, you will try to understand why it worked. Also, unless you're doing it for the theory and understanding is all you have. Anyhow, I've done this sampling for you. There are many kind of tasty things to try, and these are the most popular ones currently. First of all, there's something called ASHA, asynchronous successive halving. It's a fancy name for saying I'm going to do a random search, but because these evaluations take a lot of time, I have a chance to stop evaluations in the middle if I see that they're not going anywhere good, which means I can do more attempts in the same amount of time. Okay, that's ASHA. Second is Sambo. Sambo is sequential model-based optimization. And in there you have Bayesian optimization. And while it looks like it's Bayesian, it's almost not Bayesian. It's 3,000. And actually, there's a link here that kind of explains what it is without a lot of theory. And in Sambo, you have a model of your problem that will give you suggestions for the parameters. So it's not a random search anymore. Also, you can combine ASHA and Sambo, and we'll talk about it very, very soon. Now, there are two other types that are very popular. One is genetic optimization. This way, you change a few, you do mutations, exactly like in other genetic algorithms. You do mutations, you have generations, you change a little bit, whatever succeeds grows into the next generation, and whenever it's not, it's killed off. There are specific kinds of problems where this works well for. We're not going to discuss it today. And lastly, there's a new kid in the block. It's called population-based training. It's all the rage now, because what you're doing here is you're training your model and you're doing hyperparameter optimization at the same time. There's a link here to explain it. I'm not going to go into it. I'm not sure it's useful to tackle it in a introductory / best practices lecture like this, but know that it exists. Also, it does not apply well to all problems. Okay, so once you've taken this black box optimization, the AI algorithm changes. Okay, you have two new steps. Okay, one is an ability to do early stop, that's stage number 3. And second is the ability to put feedback. Okay, if you get the score or the taste of the cookie, you can put it somewhere and make an informed decision about it. And these two steps are what's interesting about hyperparameter optimization. This brings you from random search to successful search. Okay? Now, this is a very good place to see if there are questions about this. Okay, let's see if this works. Please answer the poll. Okay. Okay, about 50% of you voted. 57% voted. Okay, we will converge on the voting. And, oh, we have more people voting. Thank you. I think 30 seconds is enough. Oh, more people. Oh, great. Okay, so most of you understand. Those who do not understand, hit me up on Slack, Twitter, Reddit, whatever. It's the same handle, LSTMyao. I can make sure that you got through this part. Okay, now the next part doesn't assume that you understand anything about what we've just said. Okay, let's go and go back to the presentation. Okay, so we were in space with the computer. Now we're back on Earth with us. And we need to do hyperparameter optimization for our problem. What do we need? I hope that by the time we're finished here, you will want to do hyperparameter instead of anything else. Okay, so you need an efficient search pattern. That's to save money. You need a way to do parallel search. Okay. Some Doctor Who jokes in the chat. This is the wrong canon. I'm sorry. So you need to do a parallel search to save on time. You want to do manage experiments because you need to keep track on your work and do some reporting on where did all the money go. And eventually, as I said, you need to have a result, and you must have a result, and the result must be good. Okay, how do you do it? Well, you need to change some of your code. And the amount of what you're trying to do will dictate how much of your code needs to change. Okay, so if you need to input model-based parameters, you need to set up a way to put these parameter suggestions from the model inside your training, for example. If you want to do performance-based pruning, which you must, by the way, you need to make a way for the manager of the process to stop your runs, and you need to inform of the decision. So this is a prerequisite. You need to report the scores of your experiments somewhere. Okay. You don't need to understand how optimization works. You don't need to understand any of the methods I told you. These are musts. Okay. Now, some terminology, so we can speak like all the experts. A parameter, in the sense of hyperparameter optimization, is in fact the hyperparameter itself. So that's confusing, I know, but if you're doing a hyperparameter optimization, the optimizer looks at the hyperparameter as a parameter. Now, there's the objective function, which is the thing that you're trying to optimize. For example, the loss of your model. And the loss value is the value. Now, trial is a single evaluation of this function. So, for example, you're going to do 6 epochs of training. The last value of the loss will be the trial evaluation. And if you're doing many trials, which you should, it's going to be called a study. Okay, there was a Q&A. Let's see if it's something important. You're training large data, it takes a very long time to train. Okay. That's a good question. I'm going to answer it later because I want to make sure that we get to all the parameters, the data, the slides, sorry. Okay. Now, if you're just starting out with hyperparameter optimization, you would need to learn how to select these parameters. Again, these are the hyperparameters. You need to choose the correct hyperparameters to optimize. You're going to define the ranges and the sampling ways for these parameters. Then you need to somehow connect the loss function to the optimizer. You need to be able to create the study, then run it and make sure that it does this pruning or early stopping. So what I'm saying is, what if you didn't have to learn all of this? What if you just needed to learn a bit? And this is where MLOps come into play. And if you've been in my previous talks, you know about MLOps, but I'm going to make a small stop here. MLOps is the mission of taking your data and turning it into a model in a reproducible way. It's called provenance. And inside there is research, and research deserves its own MLOps because research has different tasks than production. And in there's automation. There's a bunch of data stuff that I talked about in a previous webinar, and reproducibility. And lastly, orchestration, which means starting and stopping experiments. And this is exactly what we need, right? If we have something that can start and stop experiments, and it can handle optimization for us. And what does it need? And you can screenshot this slide and get it to your DevOps person, or if you need to do it yourself. This is basically what you need. You need some kind of database and scheduler that are linked to the optimizer. And this way you can actually do parallel search, because if you're searching different areas of the search space, you can do it at the same time. You need a way to show results, tables, visualizations, and most importantly, parameter importance. In terms of DevOps, you need to be able to run Dockerized or at least cloud agnostic versions of your training, because you're going to run it on whatever hardware that's available to you. There's a lot of calculations to do. And you need to make sure that other people in your organization that are trying to do research will not be affected by your work. So you need to be able to work in queues. because you're going to do lots of restarts in the same remote GPU is going to start different trainings, you need to be able to cache the data. So you won't have to start each training by download the data set. For metrics, you need to have also usage tracking and hardware monitoring to make sure that stuff is not hanging. And lastly, you need to be able to stop, pause, and resume the optimization process. And maybe even, I'm not sure that's a good idea, but people sometimes want to be able to scale up to more GPUs within a GUI. Okay, so take a mental picture of this, because I'm going to discuss something that gives you most of this for free soon. Okay, here's soon. We have a platform, as I said, it's called Allegro Trains, but we're going to change the name in a few days. I'm going to talk about it. And inside, the way we thought of managing all of this is by wrapping whatever optimizer that you're using with basic commands to the scheduler. So defining a hyperparameter is basically defining the argparse argument that you used in your run, for example, learning rate, and defining the metric to follow and optimize. It's just saying the title and series of the metric in the tensor board. Then you can actually choose the number of concurrent tasks for parallel searches, how much time to expend, if there's a time limit for every run. And you can do minimum iterations, maximum iterations, everything you want, okay? And there are probably more detailed ways of doing it, but this is the most, I think, flexible way for the user. And then to actually do the hyperparameter optimization, you just do start. And start what? It's just a task in your experiment platform, experiment tracking platform. Now, sorry for being so brief about it. We're a little bit short on time, so I'm not going to do another poll now. Basically, I have questions here. Yeah, approach has already been selected. Yeah, so everything I just said on Earth, not the cookies, is that we have a problem, whatever problem. It could be a problem in deep learning, machine learning. It could be in the real world, okay? And we want to solve it by having an objective function to minimize and some mechanism to offer us parameters. So it could be reinforcement learning, it could be deep learning, it could be whatever. And if it's within our realm of machine learning, you better do it on an experiment tracking platform with a scheduler and MLOps solution that I just showed, because it makes much of your work makes much of the work for you. Now let's go back to space, because there's a kind of philosophical argument that I want to make here. Now, the story about optimizing for the cookies is actually a true story, okay? It's work, when you can see there's a link here, work from Google Brain, where the theoreticians went to do an experiment. They said, okay, we developed a Bayesian optimization model for Google Cloud, I think. Let's use it to make cookies. And they made 144 experiments, and they actually used the model to optimize in real life. And they shared results. And I think that most of you have never seen this kind of graph. It's called a parallel coordinate plot. I think it's evil, and it's necessary evil. It also doesn't tell you a lot if you can't use it interactively. It tells you a little bit about the optimization that took place, okay? They had, for example, brown sugar fraction and chip type, and mostly the computer converged on dark being the good taste. Basically, the taste is this, it's people reported the taste. And also high amount of chocolate, low amount of sugar relative to others, at least half a teaspoon of vanilla, and you get a spread of results. Uh, there's not much to it. Basically, if you're finishing a research, you would just say, okay, I want this value because it's the highest. Let's go see what the hyperparameters are. If you're doing more complicated work to try to understand if you missed anything, and you should, then you're going to do some more investigation of these plots. Now, why am I coming back to this research? Because they actually gave insights. And I was reading the first insight. They said, okay, we learned that we need to use transfer learning. What does it mean? It means that we do a small batch of cookies to see that it's okay, and then we do a big batch of cookies to save time. That's basically early stopping, but it's in a more broader concept because they can use information they've learned from, for example, experiments without vanilla to experiments with vanilla. And sometimes it works and sometimes it doesn't work. But I looked at it and said, okay, my official training, my PhD is in chemistry. I made the transition to deep learning after I graduated, and I did some experiments in my when I was young, and that sounded to me like those theoreticians. They started to understand what it means to do experiments in the real world, and I kept on reading. And well, they said sometimes we had some very low levels of butter, and we couldn't even make cookies. So there are sometimes that the computer will give you infeasible values that doesn't do anything, and we should try to recognize them and save time. And they also gave their insight about what it means in deep learning. For example, if you have a very high learning rate, sometimes your training diverges, okay? And I said, okay, you know what? This is exactly like in real research and real experiments. After you do enough of them, you know what will work and what will not work. And then they said, when baking, sometimes you're running low on ingredients and you have to make kind of adjustments. And I said, whoa, that's exactly like real research. And it translates to sometimes the user make mistakes, something the algorithm has a hiccup, or maybe your run has a crash or hang, and you need to deal with it during your research. And if hyperparameter optimization it maps onto real world research, then you can use real world research rules about this. And I give you my no bullshit method for research that works on hyperparameter optimization. And it means that if you have a problem to solve and it has hyperparameters and you're not sure if you have the correct ones, hint, it's never the default ones, then you can go and do this method to follow a result. And this method is good because it learns as you keep doing the research, you gain more domain expertise and you unlock more stages. So let's go over it quickly. First, never think about how much it costs, okay? But sometimes only think about how much it costs. You might ask me, Ariel, why don't you just, instead of these two lines, just write optimize for cost? Because then the entire optimization process would be for cost, and you're trying to optimize for a metric, okay? So you can't optimize for two things like this. It won't work. So it means that when you're thinking about the ideas, you shouldn't be thinking about the cost, but you should be thinking about the cost when you're actually doing the optimization. Now, use a black box method, even for real world attempts. Why? Because then you won't be tempted to project your biases on the research. Even if you think you know object detection and you know that the batch size should be 32 and only 32, or that the Adam starting learning rate should be 4 or something, like Karpathy jokes around. Okay, use the model even on values that you think that you know. On the maybe you waste some money, maybe you'll gain some new insights. Now, unique trials. It means that when you're doing two experiments, they shouldn't be too similar. What does it mean? For example, if you have an adjusting learning rate and you have an initial value that you're optimizing, changing the initial value by a little bit doesn't tell you a thing, because just the adjustment will be different. So you just need to increase the grid spacing on your parameters. Or if you're doing two consecutive hyperparameter optimizations, make sure you're not repeating any experiment. Sanity tests. In chemistry, we also call them smoke testing. Okay, you need to incorporate some way of thinking within your experiment. And am I optimizing? And am I getting the correct result from the optimization? And there's also a nice story here, but we'll keep it because it took too long in the lecture. History lessons. Well, Bayesian methods are history dependent. Okay, so if you're doing black box method with a model, you have history. But what I'm talking about here is a greater history lesson. You need to be able to search literature, talk with co-workers, people that have organizational knowledge, try to find out if somebody already did what you're doing, because it could, or something close to it, because it could give you insights. And as we said, infeasible experiments should be outed, and you only know what's infeasible and what's not if you're doing it enough time. And lastly, transfer learning is like the ultimate. If you've done an hyperparameter optimization and you need to do something quite similar, you know where to start. And if you think about it, if you really want to make things simple, you can collapse this no bullshit method to 2 stages. One is not thinking about the money, and 2 is trying really, really well to do searches with more searches with less resources. Okay, I hope this is helpful for you, because I mean I haven't seen a lot of this kind of meta discussion on hyperparameter optimization, and maybe it's because people that give lectures on this are theoreticians and not experimentalists, and this is basically doing a very, very well documented experiment. Okay, now trying to finish things off. These are warnings that will make sense if you have some experience in machine learning. But also if you do not, it has a little bit of sense, okay? So define your metrics well. What do you mean well? I just said, you know, optimize for the loss. But what if you don't want to optimize for the loss? What if you need something different? You need to make sure you have a sanity test that what you're optimizing is good. I have a nice story about this. Let's say you have an object detection model, and you have a specific test set that has a lot of people in the same image, and you're missing some of those people, and you want to optimize to hit more of them. So maybe your objective function is the number of people on the image, total number of people, and you want to maximize it. And that sounds like it should work, but what could happen is that your algorithm would find a way to exploit and remove all the thresholds, so and everything would be counted as a person. So you have a bajillion persons in the image, and none of them would be a person, but you think that the optimization went well. Cross-validation, something you probably know if you're doing classical machine learning. It means that if you have a large data set and you've done hyperparameter optimization, you should make sure that whatever you chose for the holdout set doesn't mean that the hyperparameter are valid only for the portion that you split it. Okay. You know what? That wasn't a good explanation. I'm not good at explaining this part. If anybody needs more explanation about this, I can point them up to a good write-up on this. Now, lastly, you need to remember that the 3 bad searches, the grid search, random search, and God forbid it, manual tuning, exist. And sometimes it's okay to use them. And these sometimes Unless you have lots of experience, the answer is never. But if you have some experience, you will probably be tempted to do manual search, and then the answer is never. And then if you have super experience and you're tempted to do grid or random, then random just add fancy random, and then you don't need to do it. And grid search, it's reserved for, as I said, very special considerations when you need to check out combos and you don't even know the metrics that you want to follow. So grid search is very good for that. Okay, now take home messages. As I said, always do hyperparameter optimizations. The hint, you're going to use a program called a library called Optuna, and in there you're going to use the tree parser estimator. Always have research MLOps and use our platform called Trains right now. It will change its name soon. Always have good pruning because that ensures success. And as I said, always think about having impactful results. Even 2% improvement in accuracy is a very impactful result if you present it in the correct way. Now, as I said, trains. We have an open source solution. And basically, if you don't have DevOps that will do it for you, you can get most, like 99% of the checklist that I gave just by setting up trains. It's open source, it's free. And it will do, all you need to do is just to connect your code, and it's very, very simple. And there are demos on how to do it. And and then you need resources, you need compute, right? You can't do hyperparameter optimization without compute. Okay, now, here's a link to a very excellent technical introduction about hyperparameter optimization by the people that created Optuna. Why Optuna? Because it's from Preferred Networks. These are the guys that came up with Chainer, that was the precursor to all the good ideas that PyTorch and TensorFlow are adopting. And we also have a blog post featured by PyTorch on how to use this open source trains with Optuna to do hyperparameter optimization. And we also have always running demo app that you can actually use and print results onto if you don't care about other people watching. And this is a live link. If you press this, it will open an actual hyperparameter example from the blog post that you've seen. And you can actually explore and see how it looks like when you're doing optimization. And you have tables and sort, and you can sort by objectives and batch size. And there's even somewhere here a coordinate plot, but I don't have time to show it. So just go and press the link. It will ask you for a name. Just give it any name, and you can start looking at it. Where were we? Again with this. Sorry. Okay. Now, since we're live, let me just give you a heads up. There's going to be a Stanford seminar very, very soon. There's a link to the live webinar about SBO, whatever. One of the new, very, very exciting methods for optimization that I think are going to maybe replace the tree parser estimator as the good ones. I mean, whatever Polycheck does is good, so go listen. And also, we had a competition about black box optimization, and the results will be, it's not we, so the community had. And there were very nice entries, and the results will be announced in NeurIPS. Well, actually, the results are announced. Maybe the write-ups on the results will be announced. So it's happening soon, so pay attention. And with this, I'm done. And we have questions, so let's go and answer them. Okay. So let's see. I'm going to paste the link again to the presentation just in case you missed it. It's this one. And okay, I think the question was moved here. Okay, So Leon says, well, if you're training with large data sets that take very long time to train, is it practical to apply these HPO approaches to small samples of the data? Well, Leon, first I'm going to refer you to the first webinar in this series, webinar number 1. It talks about the diminishing returns of data. Sometimes, even if you have a large data set, you can get you can get a subset of the data set by random sampling that gives you a hunch of the capacity of the model that you're training to train. But otherwise, if you're just taking a small portion of the data set, what you're going to get is you're going to get overfitting of the data, of the hyperparameters to the data. So if you're doing it, you need to do cross-validation. You need to take lots of slices from your data set and train. And sometimes it will take you less time. Sometimes it will take you more time than just running on the entire data set. But also, you can also use, as I said, timing. You can say, okay, if you don't get to a very low loss within 1 hour, just kill off the experiment, and you can take care of much of the search space, especially if you start from a pre-trained model. Rock says, say a typical deep learning lasts 2 hours. In general, how long should a medium well-done hypermap optimization take? Please don't say 42. Okay, so you didn't say how many GPUs you have, because if you have 1 GPU, it could take forever. If you have 2 GPUs, it could take 2 days. Typically, it depends on where you are in the process and how good default values are in describing, solving your problem. If you're just hunting for the last 2% of accuracy, it could take a long time. If you have something that doesn't work quite well and you want to see if it works well, it could take shorter time actually. Okay. Bill says he has to go. So I'm going to, he likes the grounded examples, like the pause. So, okay. Okay, that's not a question, so I'm not repeating it. Thanks, Bill. Speher says, beginner in machine learning is implementing neural network as code difficult as designing the architecture. No. Okay. We are, maybe 5 years after TensorFlow was released, in a situation where you can take copy-pastable code that runs a network and apply it to research and get meaningful results. Okay, you just need to have enough of your basics, let's say, covered, so you can make sense of what you're getting. Just excuse me for a second. Designing the architecture takes forever, and unless you're getting paid a lot and you have lots and lots of GPUs to spare, don't try, because somebody else will just find something better. What I do suggest is looking over at papers with code, paperswithcode.com. You probably know this. They have a lot of explanations of models, and you can find something that works, and maybe just tuning it with hyperparameters to your problem will do all the difference. How do you use optimizations for deep reinforcement learning? Okay, so should I go into it? Actually, it's a little bit late. Kanta. It's almost the same. Okay, if you have a reinforcement learning script that makes all the runs, you just use that as the entry point for the hyperparameter optimization code. And actually, the link that I sent for the Stanford talk, I think it's going to touch exactly about this, and you can ask it there. These guys are like super smart, and I hope this answers. Okay, more questions in the chat. No. People were raising hands. Were there people waiting to speak? No, right? No. Okay, great. So do share this seminar, this webinar, the link to the slides, and when the YouTube comes out, share it with your friends because it's going to be useful for everyone, I think. And thank you for joining me. Now, special treat. I alluded to it a little bit. We're changing the name of the product. It's going to be called ClearML, and we're going to be launching a free. I mean, this open source needs a server, right? We're going to launch like a free software as a service solution that will enable you to just skip this installing the server part and just connect your machines and start working. It's going to be somewhere before Christmas. So it means that in the last installment of our series, the next meeting that we meet, I think is January, we're going to have a live coding event where we do some hyperparameter optimizations and and pipelines. And if you're registered to this seminar, you're going to get invites to the early invites to the platform, so you could actually do live coding with me. It's going to be very, very nice. Okay, so thank you very much for coming. And Bill, I give you back the remote.